now being recorded. So today we're going to start a new topic, and I don't know if we'll finish it today, or we might need, like, maybe some portion of a next lecture. But the topic is going to be about optimal expanders. 1 second. Sort of check screen. Oh. Okay. Good. So optimal expander. And basically what we're going to try and ask is, what's the best we can hope for? I mean, what's like the dream expander that we could hope to get? And in particular, so just to remind you, so we'll all be talking about sort of deregular graphs. And we're going to assume there's going to be some lambda spectral expanders. And really what we're going to try to do is understand the tension between D versus lambda. So we want D to be as small as possible, but we saw, for example, in applications, as part of the graph is we need less random bits to choose like a neighbor, and to use this for pseudo randomness applications. And in general, this part of the graph here somehow it seems to be, a stronger construction. If it is, it's a very sparse graph, but it looks like a dense graph in the spectral sense. And so you want D to be as small as possible. On the other hand, we also want lambda to be as small as possible, because the smaller lambda is, the closer it is to 0, then we have like a stronger expansion guarantee. And we've seen like spectral expansion, we thought that this sort of implies other notions, like, for example, edge expansion. And we'll try to understand the tension between these two things. And in particular, we're going to prove a theorem that's going to give us the best possible trade-off between these two parameters. So there's going to be some formula that at the beginning should have no intuition why it's true, but then we're going to start to build intuition to understand why this is what we'd expect to get. Maybe just one piece of notation before we'll start is that, so far we've been working, when we talked about graphs and we analyzed their spectrum, we always use the normalized adjacency matrix, where we take, the adjacency matrix and we just divide by the degree D. Now for this topic, it's actually be easier, more convenient to work with a non-normalized adjacency matrix. So just notation here. So, if G is a graph, I'll use MG to denote it's unnormalized. Adjacency matrix. And this is just a standard adjacency matrix, right? So, MG symmetric. So the UV entry is either 1 or 0, right? 1 if UV is an edge, and 0 if not. So now this is even easier than before. Now we don't divide by D. Before we divided by D, because it made sense for analyzing random walks and to normalize lambda between 0 and 1. Now we don't want to do it anymore. So for this topic, when I want to talk about lambda of G, I'll really be talking about lambda of MG. So this unnormalized adjacency matrix. So its range, or this is all the eigenvalues. So the range is going to be, so before it was between -1 and 1. Now because we don't divide by D, we need to multiply them by D. That's going to be between -D and D. We just scale the square factor of D. And in particular, you know, lambda 1 is D. So lambda 1, to remind you, is the eigenvalue corresponding to the O1 eigenvector. So before it was 1, now it's all D, because if you have a D regular graph, you multiply with the O1 vector, you can get the OD vector, because every node has D neighbors. So this is just a bit about scaling. I mean, for this topic, it would be more convenient to work with this. And the main theorem we're going to prove here, starting today, I don't know if we'll finish today, is what's called the Alon-Bopanna theorem. That says that if G is an n vertex D regular lambda expander, then lambda cannot be too small. So lambda is at least going to be, let's see if I can just write the formula here to make sure not to make a mistake. It's going to be twice the root of D minus 1. Okay, so that's what there is. It's a formula. It's a simple formula, right? And the first thing that you want to ask is why? Why this specific connection? Like, why is this in the right thing to look for? So what we're going to do to understand it is going to do it in two parts. So part one will be talking about this plus, some low order terms. So maybe it's going to be minus little o n of 1. So this little o n of 1 is some function that decays to 0 as n goes to infinity. So if you think about d as a constant, let's say d is 10, then this says that for any 10 regular graph, lambda is going to be at least, what is going to be 6 minus some term that goes to 0. So for very, very large 10 regular graphs, lambda has to be at least, about 6. And really the way this is going to behave is something like 1 over log n. I'll talk more about this error term later, but it's sort of, it goes to 0. Not super fast with n, but somewhat fast with n. Okay. This is this error term. Part one, we're actually going to talk about something called the infinite D-regular tree. So the infinite D-regular tree is to some extent like an infinite model for D-regular graphs. And we will see that this is in terms of expansion, it really is the best we could hope for. And we're going to see that we can analyze its spectral expansion. And first of all, we need to define what does it even mean to talk about spectral, expansion for an infinite graph. So we'll talk about that. But for this graph, lambda is going to be exactly 2 root d minus 1. So somehow for this, the nicest case, the simplest case, this infinite tree, we're going to get exactly this part, this bound for lambda. And then the second part will be to analyze, so show that the finite graphs cannot be much better. Much better. So we'll see proof techniques that allow us to analyze finite graphs and to some extent show that whatever bound we can prove for this infinite D-regular tree already transfers to finite graphs which are D-regular. So this will be, again, D-regular and much better than the D-regular infinite tree. Okay. That's going to be conceptually the two parts for this topic. So first we'll analyze this infinite tree, prove this, but we exactly compute lambda for it. And then we see how we can transfer these results from this infinite tree to finite graphs, which might be surprising. Like, why would something that's true for an infinite graph, and it's just a one, it's just a specific graph, why would that transfer to any deregular graph? That's going to be another conceptually interesting, point here. So before I start talking about the proofs, are there any questions on this high level? What we're trying to prove, and this high level approach.
One question. So it is a two-sided lambda expander graph, or just one-sided?
Two-sided.
Two-sided.
It's going to be two-sided.
Thanks.
You can also prove bounds for just for the one-sided case. You can prove bounds for lambda 2. So actually, what Alon and Lupana proved is, well, I'll get to it later, but they proved it for lambda 2. But that proof is somewhat more complicated. We're going to prove a lambda, which is going to be a weaker result, but easier to prove.
Thank you.
But yeah, I'll mention that once we get to it. So really, the bound here is not on lambda, but on lambda 2. So which even it could be that so not only we're not saying that the negative ones are very negative, but even the positive ones have to be somewhat big. And we've seen it for some questions. Lambda 2 is really the interesting object we're trying to study. So in fact, you're going to see a question in the second homework where we analyzed mixing, and to analyze mixing we used lambda, but actually if you make the random walk a bit lazy, you can show that you can transfer all the way to lambda 2. So if lambda 2 is bounded, even if lambda is, let's say, very large, you can still analyze mixing. But again, that's going to be, you'll see that in homework. That's a good question. More questions? Now I'm going to go to part 1. So first I want to tell you, what is this deregular infinite tree, and how do we analyze, or how do we even define the spectrum of infinite graphs? But before that, let me tell you about this what is this infinite tree? So as the name suggests, it's a tree, it's infinite, and it's deregular. So there's not too many things you can do here, right? Let's say if I want D to be 3 here, say for a good example, so I choose some node to begin with, and I say, well, it should have 3 neighbors. And then each one of those, it already has 1 neighbor, it should have 2 more neighbors. And each one of those should have 2 more neighbors. And so on. So this is, and I guess I forgot somewhere. No, I think that's okay. So this is like a 3 regular infinite tree, and you keep going for infinity. So there's actually a convenient way to think about it. Maybe it's a concrete way of thinking about it that I think, to me at least, is convenient, which is if I choose a specific route to this tree, I can identify nodes with finite walls. Just conceptually easier to think about it. So let me give you now a formal definition. So maybe before that, I'll do a picture here. Again, this will be for the 3. So here I'm going to choose one node to be. So I'll do the picture here, and then I'll start out the definition. And again, I'm going to use 3 as my concrete example. So on. So I'm going to choose a specific node to be rooted. So here's going to be the definition. Or maybe before this definition, I need one reminder. So if sigma is a finite set, then we denote by sigma star all the finite words, with alphabet sigma. So this is just probably you've seen this in some previous, classes, undergrad or something. But so just for any finite alphabet, sigma star is just all the finite words. So the way we're going to identify this tree, so I'm going to first do it sort of by picture, then I'll write the formal definition. So in this case, that's going to be 3. So I'm going to think of the root as being the empty word, and we're also going to use epsilon is going to be the empty word, just a standard notation for the empty word. So the root is going to be epsilon, and then I'm going to do 3 nodes. I'm going to call them 1, 2, 3. And then from this point, each one has 2 nodes. So this one is going to be 1, 1, 1, 2. This one is going to be 2, 1, 2, 2. This one is going to be 3, 1, 3, 2. And then you're going to have a length 3, length 4, length 5, and so on. So what we can do is identify all the nodes of this infinite tree with finite words. But there's one small caveat where the first character has 3 options, or in general, D options, but all the other characters have D-1 options, because at every node that's not the root, so only D-1 options is going down, so further away from the root. So now we can define, so here's going to be the definition. So the D regular infinite tree, and we're going to call it, again, I want to use the same notation as in the note, we call it TD. It's an infinite graph. So it has the following vertices. So it's going to have vertices. It's going to be, well, you could have the empty string, or we could have, let's write it, D times. So the elements of this is either the root, the empty string, or a node, and a node is identified by a word, where the first character has D options, and all the other characters have D-1 options of some finite length. And what are the edges? The edges are all these pairs UV. Let me also denote by so for V and V, let me denote by this to be the length of V. Just the number of characters in V. Its distance from the root, right? So it's going to be where the length of U is the length of V minus 1, and the prefix, and maybe let's split at that, and V equals U concatenated with some character C. So again, this is just a formula of writing that, what are the edges here? They go from a word to a word of length 1 more, but adding 1 more character. Right? So again, this is just I think this picture sort of explains it even better, right? You just have words and you keep going down. So this is the D regular infinite tree. Are there any questions on it so far? What is this graph?
Hey, Shah. I'm still a little confused on how the vertices are labeled here.
Okay, so the vertices are labeled. So let's think, the root here is labeled by the empty word, and then it has 3 children.
Yeah.
So I went this tree down, so I'm going to call them 1, 2, 3 because it's going to be 3 regular. And then what are the children of 1? It's going to have 2 children. It has 1 parent. So it'll be 3 regular. So I'm going to call them 1, 1, 1, 2.
Okay.
And then 2 is going to have 2 children, 2, 1, 2, 2. And 3 is going to have
same with 3.
Like for example, 1, 2 is also going to have 2 children, 1, 2, 1, and 1, 2, 2.
Oh, okay. So when we write like B is equal to like the epsilon, that is the empty string, union like D times D minus 1 star. What does the D minus 1 star mean?
Oh, this is exactly where is it? What I wrote here, right? So for any finite alphabet, sigma star is the set of all finite words over sigma.
Oh, okay.
Basically, for sigma being the set 1, 2, 3 up to D minus 1.
Oh, okay. So D minus 1 is just like removing like 1 like alphabet from the.
Yeah, I mean maybe I thought you all know this notation, but just so that just so when I write, let's say D, that's just a set 1 up to D.
Yeah.
I think we've seen this notation also in other cases.
Okay, got it.
Yeah, so just remove one of the characters, just have d minus 1. It does
Okay.
mean, yeah.
Got it. Thank you.
Sure. Any more questions? Okay. So maybe the first thing before we try to analyze a spectral expansion, let's try to look on the edge expansion. Okay, so now the first question I want to ask myself, what is the edge expansion? This TD, right, of this infinite deregular tree. So how do we even define edge expansion for infinite graphs? Well, it's exactly the same as we did finite graphs, but we always look on finite sets of nodes. So it's going to be, so the edge expansion of TD is going to be the infimum over all finite sets of nodes, finite, of what? Of the edges that leave S, the edges from S, its complement, over the D, the side of S, right? This is a way we defined it for finite graphs. The finite graph says that S should get most half the nodes. Well, here there are infinitely many nodes, so this is sort of an obvious restriction. But we do want S to be finite, and all these calculations are meaningless. It's like infinity divided by infinity. Because this is how we define edge expansion for infinite graphs. And what is this in this case? Well, let's see. How many edges does S has to its neighbors? So here's a claim. So I'm going to claim the following thing: that the edge expansion, this infinite deregular tree, is actually better than what we could get for any finite deregular graph. It's actually going to be d minus 1 divided by d. Okay, so we're going to prove this in a second. I just want to remind you that if we compare, so okay, actually let me compare it to finite graphs in a second. But so okay, let's see why. Let's first prove it, then compare to the finite case. So what's the proof? So
sorry, d minus 1 or d minus 2?
d minus 2 divided by d.
Okay.
Let's see why. So let's fix some finite set S, B, and let's ask, well, how many edges could we have inside S? So I claim that because it's a tree, we could have at most S minus 1 edges, right? So the size of the number of edges between S and S is at most S minus 1. Because it's a subset of it's a sub graph of a tree. So if it's connected, it's going to be a tree. So it's going to have S minus 1 edges. If it's not connected, it's going to be a forest. This joint union of trees is going to be even less edges, right? That's like so the largest number of edges is if you choose it to be a subtree. So what does it mean? What's the number of edges from S to its complement? Well, every node in S has D neighbors, right? It's going to be ds minus, and it's going to be twice the number of edges from S to itself, because every edge from S to itself we need to remove twice. Once from one node, once from the other node. So this is going to be exactly, so let's just say this is at most S. And that's going to be, at least D minus 2 S. So now if we divide by ds, we get about. So that's it, that's a calculation. And what I want to point out is this is better than what we could get for finite graphs. So just to recall, that for finite deregular graph G, edge expansion of G is at most, so it was D was at most half, sorry. Right, this was one of the questions in the homework, right? That any finite graph, basically we're choosing S to be a random set of half the nodes, is going to give you edge expansion of about a half. So we see already that in that sense, this infinite graph is better than anything we can get in terms of edge expansion for finite graphs. But this doesn't tell us anything about what can we say for for spectral expansion, right? That's even less clear. How do we compare spectral expansion between finite graph and infinite graphs? And that's what I want to tell you about. How do we first define the spectrum of infinite graphs? How do we compute it for this d-regular infinite tree? And then how do we use this to understand the spectrum of finite graphs, d-regular graphs? But before that, are there any questions on this edge expansion for this infinite d-regular tree? No. Okay, perfect. So now we can move to a new topic. Let's call this topic spectrum of infinite graphs. And what I'm saying is true for any graph or any infinite matrix. But what we want to assume that every row and column has a finite support. So let M to be Mg. So the unnormalized adjacency matrix of some infinite graph. But what I'm going to say is more generally, you can assume that any row or column of M has finite support. So only a finite number of non-zero elements. When it holds in our case, for this d-regular infinite tree, every row and column has just d entries equal to 1, the rest are 0. But what I'm going to tell you about holds in this more general sense, so not just for graph. And what we want to do, in general, when we talk about spectrum, we want to look on these matrices as linear operators. So in general, we say, what is a matrix? A matrix, like an n by n matrix, is a linear operator from Rn to Rn. So what we want to say that M should be a linear operator from R infinity to R infinity. But R infinity is not well behaved enough. So turns out we need to somewhat restrict the type of vectors that you're allowed to take. So turns out what you want to do is just restrict to vectors whose L2 norm is finite. So let me define it now. So if I have V, so if V is some set, like for example, the vertices of this infinite graph, L2 of V is a set of functions from V to R, such that the sum of V squared is finite over all V and V. Right now we have infinitely many coordinates, so we can just say take any vector. Say we'll take any vector whose L2 norm is finite. Okay, and we're going to think of M is going to be a linear operator from L to V. L to V. And here we're assuming this actually uses the assumption that every row and every column has finite support, and actually also you need them maybe to have some bounded maximal value. Bounded maximal value. Like in our case, it's 0, 1, so it definitely holds. So you should take sort of vectors of finite L2 norm to another vector of finite L2 norm. Okay. And we want to define eigenvalues. This is sort of how we view it as a linear operator. What's going to be the spectrum? So the spectrum of M. So what are the eigenvalues of M? It's all this lambda. Let's see. All these numbers lambda in R, such that if we take the matrix M minus lambda I, it's going to be singular. So I'll define singular in a second. What does singular mean in this case? But notice that for finite matrices, this is exactly the definition of a spectrum, right? So if you remember from your linear algebra classes, an eigenvalue is exactly a number lambda such that M minus lambda I, is singular. Now, what does singular mean for finite matrices? It means, for example, that it has an element in its kernel, or that its image is not everything. Right? So, I mean, this is sort of for finite matrices. And the question is, how do we define singular for infinite matrices? And in general, so here's going to be a definition. So matrix A is singular. Say so matrix A, again, acting on this L2V, is singular if its image is not everything, right? If its image is not everything, it's not full. In other words, A times L2V is a strict subset of L2V. So I cannot get all possible vectors by multiplying by A. Okay, so this is sort of one way of defining singular. But turn out that's a correct way of defining singular for infinite matrices. So I should not be able to get all possible vectors in the image. You can also talk about the kernel, asking either any vector in the kernel. Now, if there is a vector in the kernel, this would show it's singular, but there could be matrices, infinite matrices, that are singular, but still there's nothing in the kernel. So maybe just one example to illustrate it. Think about the matrix that maps. Let's say they have X, as you know, X1, X2, X3, and A is going to map it to 0, X1, X2, X3. So just a matrix that pushes everything down by one coordinate. So clearly its image is not everything. I cannot get anything in the image with 1 in the first coordinate, but there's also nothing in its kernel. So this sort of equivalence for finite matrices say that a matrix is non-singular if and only if its kernel is empty is not true anymore for infinite matrices. So we really want to define singular in terms of the image, whether anything is the image or not. Okay, anyway, it's a small technical point. So this was our definition of the spectrum, all the eigenvalues. So notice that here, like for finite matrices, there could be infinitely many eigenvalues. So we're not going to try to sort them out at lambda 1, lambda 2, lambda 3, but could be infinitely many, and we still want to understand the range. Okay, and what we're going to prove is the following theorem. Let's say that the spectrum, this d-regular infinite tree, is containing this strip -2, d minus 1, 2, d minus 1. And in fact, it has eigenvalues touching both of the ends, ends of the interval. So I don't know if it's known if it contains the entire interval or not. I'm not sure what's known about that, but so we're just trying to bound the maximal ones. Then we know it's going to touch both of the endpoints. Okay. So in particular, so this implies, right? It's a maximal eigenvalue of TD in absolute value is 2d minus 1, which was a bound that I claimed we have for this infinite d-regular tree. Now, this still doesn't explain why we get this specific quantity 2d minus 1, but at least now we start developing the tools to try and analyze this. So the next thing we're going to do is prove the theorem. But before that, are there any questions about any of the definitions. I mean, these are all new definitions. Any of the definitions? Any question on them, or anything else?
Could you repeat again the argument for why we define it in terms of the range and not the kernel?
Yeah, so think about this example I listed there, right? So I claim this matrix A. So what is this matrix A? So A here is going to be, it's going to map the first element to the second coordinate, right? So it's going to be, I guess, this type of matrix, right? So the 0 here, that's the ones just below the diagonal. I claim this matrix is singular because AX is always going to have 0 in the first coordinates, right?
Right.
But its kernel is empty because if AX is 0, X must be 0.
Okay.
Right?
Yeah, I see what you're saying. Thank you.
So there's these two definitions that are equivalent in the finite case, but in the infinite case, they're not the same. So this definition is stronger. More questions? So now I want to prove the theorem. And so now I'm going to prove the theorem. So basically, what do we want to prove? We want to say that if lambda is outside, so what do we want to show? So we want to show that if the absolute value of lambda is more than 2 root d minus 1, then lambda is not in the spectrum, this irregular infinite tree, right? That's our goal. What does it mean not to be in the spectrum? So i.e., what you want to show that the matrix, I'm going to use M here. So I'm going to use, so here I'm going to use M instead of MTD, just because it's easier to write. So in this proof, I'm going to use M as the adjacency matrix of the D regular infinite tree, okay? So that M minus lambda I is not singular, okay? And I claim, and I try to explain why, is that this is true. Again, what does it mean to not be singular? It means I get any vector in the image, right? But I claim that this is if and only if I can get, so the vector, let me try to use the same notation as here, you can only if delta V is in the range of M minus lambda I for any V in V. I claim that the following thing holds. Choose any vertex that you want. Actually, it doesn't matter which one you choose because this graph is isomorphic, right? All the nodes look the same. Choose any node and ask, can I get this? What is delta V? Delta V is the indicator for this vertex. It's a vector that has a value 1, right? So delta V is the vector that has the U, it has a value 1 if U equals to V and 0 if not, right? It's a unit vector. And I'm asking, can I get this one specific vector to be in the image? Well, of course, if I can't, then it's not singular. But I claim that if I can, then I can get any vector. Because, well, why? So I'm not going to write a proof here, but I'll give you an intuition why this is true. First of all, this graph has an automorphism group. Basically, it means take any node, all the nodes look the same. I mean, there's not no, but from any node could be the root of this irregular infinite tree, right? They're all, so any finite diameter looks the same. And so if this is true for one node V, it's true for any node V. And then we can just, so any node V is M minus lambda I times some vector. And then I can, if I want to get any vector whose L2 is bounded, I can sum them up with coefficients who are also going to be bounded because the L2 is bounded and everything is going to converge. So I'm not going to prove it here, but I think it's just an exercise in linear algebra. So we're just going to take it on faith. So what I want to focus on is just on this condition, saying fixed V, any node that you want, doesn't really matter which node you want, maybe the root and ask, let's prove this node, this delta of this node is going to be in the range of m minus lambda I if lambda is beyond this interval of 2 d minus 1 plus or minus. Okay, so I'm just going to focus on proving that. Okay, so how do we do that? So what is our goal? So again, what is our goal? So our goal would be to find some function f from V to R such that m minus lambda I times f equals this node delta V. Okay, that's our goal. Maybe actually now that's a good point to stop for a second. Any questions so far on the general? So now we actually can construct f by hand. But before doing that, are there any questions on the general strategy of what we're trying to do here, or any of the definitions? Okay. So how do we do it? Well, let's think. So first, we're going to make a step that's going to greatly simplify our lives. Because what is f? So let's just draw a picture here. So again, here's V, and I'm going to start drawing the tree below it, and so on. I claim that we can assume without the generality that f gets same value at every level of this tree. Why? Let's assume such an f exists. And let's average this f on levels. So I have these 3 nodes here, like for example, on first level. So if they got some values A, B, C, I'm going to just replace them all by A plus B plus C over 3. And if this nodes below it got like 9 values, sorry, I drew too many edges here. It should be 3 regular, so each one of those should have only 2. Okay, only 2 outgoing edges going down, right? So if in the level below there are 6 nodes of distance 2 from V, I can just average over all of them, and so on. Why? Because think about what does this m minus lambda I do? So I claim that this m, it's the same, right? It's sort of so okay, let's look at this identity for a second. So it says take any node, let's say maybe for example this node here, and I apply to it, and I claim that everything here is what's going to be what's going to call spherically symmetric. Just depends on the distance from V, not on the identity of the node, but just on its distance from V. Well, delta V is definitely centrally symmetric. It's 1 on V, 0 over anywhere else. Well, identity is also going to be the same, right? And what does M does? M compares a node. So, sorry. M compares a node to the node in 1 level up and the nodes in 1 level down. So if F satisfies this property, then symmetrizing F in every level will also satisfy this property. But if each node A equals, if every node times lambda equals, the sum of its neighbors, then the average of a node at level I equals times lambda equals, the average of the levels in 1 up plus the average down level 1 down times d minus 1. I mean, since we'll try to construct an example here, to construct f, I mean, I can do it in this special case, but I just wanted to explain why restricting this special case is not really a restriction. Because if we had any way of constructing an f, we could in particular assume f is symmetric. Okay, but anyways, we're going to build a construction. So even if you didn't fully understand this explanation, I mean, you're going to see construction. So we're going to now change color now. So let's assume f is symmetric in the following sense: f of a node u depends on the distance from V and U. So all the nodes of distance 1 are going to get the same value. All the nodes at distance 2 are going to get the same value, and so on. Okay, so I'm going to make this restriction, but now it's going to really simplify the space of functions that we might want to consider. So we can describe F by a sequence. The value we give to nodes at distance 0, x0. x1 is going to be the value we give to nodes at distance 1, x2, and so on. So F of a node U is going to be x of the distance between U and V. So again, V is going to get the value x0. We will do another picture. So my function is going to give here the value x0, and all these nodes the value x1, and all the nodes below the value x2, and so on. So again, it's a special type of function, but I claim if any function exists, such a function also works. So we should just do that. And now we can just ask, well, if we make this assumption, let's plug it to this equation here on the top and see what do we get. Because now we're going to get some recurrence on these coefficients x0, x1, x2, and so on. So clearly there's going to be two different cases, depending on whether we're at level 0 or at level more than 0. Well, let's see. So maybe just copy this equation here again. So the equation here was, again, m minus lambda I f equals delta v, the root. Well, let's see. Let's plug here nodes that is at some level k. Well, what do I get here? So let's say, so take this vector here and think of this vector at some node of level k. So what are all the neighbors? It's going to have one neighbor of level k minus 1, one closer to the roots. And it's going to have d minus 1 neighbors at level k plus 1. So we're going to see d minus 1 k plus 1 plus 1 xk minus 1 minus lambda xk, right, equals to what? Well, if we're at level k, which is more than 1, then this vector delta v is going to be 0, right? We're in some coordinates for some vector, some node u, which is not v, so it's going to be 0. So we're going to get this recurrence we need to solve. So again, what is the reason for this recurrence? We're looking at a node u that is a distance k from the root v. So the right hand side is 0. On the left hand side, m is summing of all the neighbors of this node. So it has, if a node is at level k, it's going to have a d minus 1 neighbor at level 1 more going down the tree, and one neighbor at level 1 less going up the tree. So we get d minus 1 times xk plus 1 plus xk minus 1 minus lambda xk, right? So this is lambda I. Now we also have one more equation. This is the base case for the roots. So if you're at the root, well, here we're going to get 1. And what we're going to see, well, minus lambda x0. Well, the root is of special because the root, you cannot go up, you can only go down. So you're going to get dx1. Okay, so overall, this set of equations define, these are the equations you want to solve, and once there is a solution to the equations as long as lambda is large enough. Okay, so before I show you how to solve the equations, I want to ask, is it clear how we got these equations? Why this is what you will get if you try to solve this n minus lambda I f equals delta v, and you restrict to f being a symmetric function, so getting the same value at every level k. So maybe take take some time, stare at it, and see if you have any questions on that. So now we basically translated the question, just solving this recurrence. And I think many of you learned in sort of some discrete math class how you solve these equations. And the way this works is the solution. So the solution, I'll just write you the solution. It's going to be the following form. Well, xi, what I say, the ith value is going to be some scaling factor. Then figure out alpha times some exponential term that looks like that. Lambda minus square root So we get that there is this, that's like the form of to the power I here, sorry. So there is this sort of, it's always solutions to such equations are always the form a constant times another constant to the I, or maybe some linear combination of those, but that's one of the possible solutions. In general, it could be lambda plus or minus, but that solution would be good enough for us. That solution is going to work for us. There are more solutions, but that's going to work for us. So if it's not clear how we got that, I mean, this is again, I'm assuming many of you have seen how to solve these type of equations in discrete math classes. So if not, you can just maybe look it up online. So but we're gonna, so this is a solution, but now we need to ask ourselves, well, is this going to be a real solution? And is this going to solve also this last equation is equal to 1? But that solution for the homogeneous cases, the one for k being at least 1, it's not necessarily, it's not obviously, it solves also the last equation of dx1 minus lambda x0 equal to 1. So what I want to do now is analyze this type of equation and see why it naturally works when this regime of lambda being more than 2 root d minus 1. So now let's analyze this. So that's going to be our solution here. Now let's analyze this. So I want first of all to point out that if lambda is more than 2 root d minus 1, then this root thing is actually then, well, lambda squared is more than 4 d minus 1. So, this term here, this root thing that could potentially be the root of a negative number, and then you get complex solutions, which we don't want to allow here, is actually real, right? Because lambda squared is large. Lambda squared minus 4d minus 1 becomes positive at this, exactly at this threshold. So that's already one good thing of why we get this natural threshold occurring. So that's one thought. So xi is xi's are all real. That's already one good thing. Now I also want to analyze them. So I want to claim the following equation. So I'm going to claim the following equation that you can prove that xi squared is smaller than alpha squared 1 over 2 to the d minus 1 to the I. I'm going to make this claim. And why is that? Well, the alpha squared just comes from this alpha. In the exciter, really it's about the element in the parentheses. And really this follows from the following identity that in general, if I have numbers y which is more than z which is more than 0, then y minus square root of y squared minus z squared is less than z. So just a simple analytical identity to verify. And then if I plug in y to be lambda, and I plug in z to be 2 root d minus 1, and you simplify, you exactly get this claim. So again, we also have this in the notes. So if this is not clear, you can review it at your own time, but just a substitute in values. There's nothing deep here. So we get this. So now we can try to ask ourselves, well, is this what can we say about this solution? What do we need to prove about this solution? So the first thing we need to prove is, so the one thing I want to prove is I want to show that indeed f is in L2V. So that, if I sum the squares of all the values, I should get something that's finite. So let's do that. So what's the sum of fv squared over all v in v? Well, there's going to be whatever f0 squared is, which is some number. That's not important. But all the rest are going to have the following form. Let's go from k from 1 to infinity. How many nodes do I have at level k? Well, I have d options for the first level times d minus 1 to the k minus 1. That's a total number of nodes at level k. Remember, nodes at level k corresponds to words where the first character has d options and the other characters have d minus 1 options. So we have exactly this number. And then we have, well, then we have times x k squared, right? So that's a value that all these nodes get. And they claim this converges. But let's see why. Well, that's going to be, again, this f0 squared, that doesn't really matter. So plus, let's plug in this xk squared, this equation we have here, so plus alpha squared. Then we haven't chosen alpha, it's going to be some finite number. What do we have? We have d. We have d minus 1 to the k minus 1, and we divide by 1 over 2 d minus 1 to the k. And you see, exactly this d minus 1 to the k in the denominator exactly cancels this one, right? So that's going to be, you see that sort of, actually with some room to spare. So we divide by a k factor, but we only multiply by k minus 1 factor. So this actually cancels that. And now we exactly get, again, this f0 squared plus d alpha squared, the sum of k at least 1. What do we get? 1 over 2 to the k, which converges to 2, right? So this is sort of, I mean, the actual value doesn't really matter. All that we really care that this is finite. So this is a finite number because this sequence converges. This geometric sequence converges. So we verify the first thing. This is actually a vector that is allowed. Its L2 is finite. And we know, I mean, we haven't shown it, but you can just plug in and see that any vector of this form is going to satisfy all these equations for k being at least 1. But that's how we derived it. So the last thing we have to do is also show that we can choose this value for alpha, so it will satisfy this last non-homogeneous equation as well. Okay, so the last thing is a different color. So the last thing that we want to show is that we can choose alpha so that this last equation still holds, which was dx1 minus lambda x0 equals 1. And just to remind you, what was the form of these equations? Xi was alpha times some number that I'm going to call rho lambda. So the I, the rho lambda was this ugly expression, like lambda minus root lambda squared minus 4d minus 1 over 2 minus 1. Right, that was our general form. And we verify these are all positive, they're all real numbers, so we just need to choose alpha. Well, I'm claiming that, well, what does it mean that I can solve it? Well, let's see. So we know that x0 is going to be, let's just write this out. plug in the values for x1 and x0. So we get alpha times d rho lambda minus 1 equals 1. We're just sort of substituting the values for x0 and x1. So what do we need? So we need, all that we need to solve it is that d rho lambda is not 1. So the last thing we need to verify that we didn't sort of get really unlucky, and this value of rho lambda happens to really be 1 over d, right? Because then we cannot solve it. So why it is not 1 over d? Well, we already saw before using the same thing that this is smaller or equal, I guess. Then again, this was this. Then sorry. Something that we already saw this is impossible. Why? So this was, I guess we saw that this is smaller than I think 1. Sorry. We thought that this is smaller than 1 over 2 d minus 1, if I remember correctly. Give me 1 second. Sorry, it's even easier, right? So think about this. What do we know about this? So what we want to rule out, that rho lambda is 1 over d. 1 second, sorry. So something here is not right. Oh, I know. I forgot this should be lambda, not 1. Okay, I was missing this. This is not 1, this is lambda. So what we want is that this should not be not 1, but should not be lambda. Just sort of substituted wrongly. But what do we know about this rho lambda? We know that rho lambda, just saying because it's lambda minus something that's negative, is smaller than lambda over 2d minus 1, which is less than lambda over d. So it cannot be equal to lambda over d. Right? Twice d minus 1 is more than d. So that's it. So we're done. So this finishes the proof. So I know there was a lot of calculations here and maybe not tons of intuition, but I hope that one thing that you got from that is that we can actually, first of all, define and analyze the spectrum of this d-regular infinite tree and show that, you know, it's bound in this interval of 2 root d minus 1 plus or minus 2 root d minus 1. And maybe, and again, if you want to sort of go through the calculation, it's probably better if you know, at your own pace, go through the calculations at home. You have them all in the notes and just verify them for yourself. And I think another thing that should be maybe unclear at this point is, okay, why was it useful? Why could we even think about the d-regular infinite tree as a model for finite graphs? Why can we use this type of analysis, you know, to analyze finite graph? Because we cannot use the same solution because the only reason this solution works is because we have this infinite sequence, so we could solve it. But this will not work for finite graphs. So when we're trying to analyze finite graphs, we need a different technique, not this technique. So this is what I want to start doing now, and we're going to sort of finish next time. And but maybe before I do that, let's see if anybody has any questions. So this finishes the analysis of this d-regular infinite tree, and the next step is going to be going back to finite graphs. So now is a good point to stop for questions. Okay, so now we can go back to finite graphs, and I can tell you about this theorem of Alon and Bopanna in a bit more detail. So let GVE be a finite graph, finite d-regular graph, and it says eigenvalues. the eigenvalues of, remember, the non-normalized adjacency matrix are number 1, number 2, so on, number n. And also what we want to assume here is about the diameter of the graph. And assume G as diameter delta. Just to remind you, the diameter of the graph is a distance to the two furthest away nodes of this graph. So for every two nodes, we look at the distance, the shortest path distance in this graph, and we're asking what are the two furthest away distance. Two furthest away nodes, this distance. So we will discuss this diameter parameter again in a second, but the way they state the theorem is in terms of this diameter delta. So then the claim is that lambda 2 is going to be at least 2 root d minus 1 times 1 minus epsilon, where epsilon goes to 0 as the diameter of this graph increases. Where epsilon is an order of 1 over delta square. Okay, so that's a theorem. Okay, so what does this theorem say? First of all, notice it does not talk about the number of nodes in this graph. So the only parameter that might be growing here is the diameter of the graph. And it said if I have a d-regular graph of a large diameter, then its second eigenvalue is at least as large what you will expect to see in this d-regular infinite tree. So this value, this magical value of 2 root d minus 1 times some error factor 1 minus epsilon, but it's epsilon to 0 as the diameter grows. So in particular, notice in particular, if the graph has n nodes and it's d-regular, we saw in the homework that the diameter is at least log n over log d. You remember that's from the homework? So in particular for constant d, so if d is, let's say, a constant, which is going to be our main interest for expander graphs, then the diameter is at least some constant log n. So as n grows, you get exactly the diameter goes to infinity, and then the lambda 2 of g is again the same thing, 2 root minus 1 minus epsilon, where epsilon is order of 1 over log square then, order of the diameter square. Okay, so that's why they get this type of error bound. So interestingly, sometimes when you study graph theory or try to prove things, what you really want to assume is that the graph doesn't have short cycles. So there's no first to go from one node to another node. But here, they don't need this. They just need to say that some two nodes are far apart. There could be short cycles, that's fine, but it's enough to have two nodes that are far apart. It's enough for this theorem to go through. So really, we're going to use this application. But the theorem, the way we're going to prove it, doesn't really talk about the number of nodes. It instead uses diameter as a proxy. So are there any questions on the theorem or this corollary? So again, the intuition here is that graphs of large diameter approach this d-regular infinite tree, at least in this spectral sense. So even if locally they don't look like a tree, even if locally they have short cycles, so they don't look like this infinite tree, when we're looking at the spectrum, it does approach the spectrum of the d-regular infinite tree, at least in terms of the largest, smallest values it can get. So what we are going to prove, and again, we probably want to do it next time, but what we will prove, so we will prove the weaker version. It's going to be weaker ways.
Actually, Shachar, it might maybe it's worth noting why here in the finite case we're looking at lambda 2, whereas in the infinite tree we're looking at all the eigenvalues. Right, so maybe it's worth explaining this.
That is a good point. Yes. If you think about for finite graphs, you also have this eigenvector of all one, right? Which again, so you can think of it as looking at the uniform distribution over the nodes, that if I make one step in this graph, I'm going to still be uniform. So the uniform distribution is a stationary distribution of the random walk on this graph. But if you look at an infinite tree, you cannot talk about the uniform distribution on the infinite number of nodes in this tree. And if you're trying to calculate the stationary distribution, it will not be that. It will be something that decays, with the distance from the root. And sort of this obstacle of lambda 1 doesn't exist in infinite graphs, only in finite graphs. Or another way of saying the same thing is you cannot take the all one vectors. It will not be bound in L2. Like it's L2 squared is going to be infinity. But yeah, Max, thank you. That's a very good point. So this lambda 1 obstacle that exists in finite graphs, so it will always be orthogonal to the uniform distribution of the all one vector. We don't have to do for infinite graphs. That's another sense in which they are simpler than finite graphs in the spectral sense. That's a good point. Okay, so maybe going back to what we're actually going to prove next time. So we're going to prove stuff that's going to be weaker in two things. So again, so G is going to be a deregular graph of diameter delta. Then what we're going to first, we're going to bundle, sorry, not lambda 2, but lambda of G. Turns out the bound in lambda G is actually easier. I'm going to get the same type of bound, 2d minus 1, 1 minus epsilon, but also the dependence of epsilon on the diameter is going to be worse. So what we are going to get, well, epsilon is going to be order log delta over delta. So the fact that epsilon, so before epsilon was 1 over delta squared, now it's 1 over delta roughly. That's not a big issue. That's a smaller issue. The bigger issue is that we're not bound in lambda 2, but we're bound in lambda. So these graphs could potentially have, very large, small eigenvalues, so very small eigenvalues, below 0, -1. But there is a way of refining this proof that we're not going to do here. But if any of you are curious about it, you can just read the paper, where with a bit more involved proof of the same general ideas, you can have about lambda 2 instead of lambda. So maybe I just want to maybe use the next 5 minutes, that's going to be the end of the class, just to tell you, in what sense can we use the deregular tree as a model for studying finite graphs, because it's not clear why is this useful. So the main thing we're going to use is the following property, which is, so it's going to be the following property. I'm going to say that the deregular infinite tree, I think it's called the cover. How is it called? A universal cover is something I'm going to call a universal cover. I'll explain what this means in a second. For any deregular finite graph. And what does a deregular, what does a universal cover mean? So it means the following things: that we can model random walks in the graph by random walks or by walks in this tree. And in the graph, I might return to the same node a second time, but in the tree I cannot. But any cycle I can form in the tree, I can also form in this graph. And the graph might have more. So let me just show you something by picture, and I'm going to do it a bit more formally next time. So again, let's look on this. Okay, so that's going to be the infinite graph. And let's say now I'm going to have a three-regular graph. So maybe I'm going to something like that. And okay, so here's a three-regular final graph. So first I want to say, well, and let's say I want to look on cycles that start here. Okay. So I'm going to say, well, I'm going to map this to the root of this tree. And then I'm going to say, well, this node has 3 edges. So I'm going to call them, let's give them this. Let's call this 1, 2, 3. So I'm going to call this node edge 1, edge 2, edge 3. Okay, so then if I go from this node red, so from this red node now to this node, I can map this to this node in this tree. And now maybe from this node, I want, now again, I have 3 edges going out. And again, let's give them names. It could be the same names before, or it could be different names. So it has 1 is going back. But the other 2 nodes are going to go down. So let's give them names, let's say 1 and 2. It corresponds to nodes, edges 1 and 2 here. So maybe now I want to go to node 3, so I'm going to take edge 2 here. So now I'm going to go to edge 2 here. I'm going to go to, so this would be, let's call them A, B, C. It's going to be here, A, B, C. And and I can keep doing that. Like, for example, here, if I want to go from C to A, I will not jump to the root, but I will say, well, A is just to be another node, so now it's going to be here. So this is going to be, I'm going to give this a new name, D. This is going to map here, D. So I can keep going down this tree infinitely many times, and this will correspond to any type of walk I can take in my graph. The only thing we're going to actually go up is if I decide to go back on an edge I came from in the graph. So if at this point, if I went to D, and then I decided from D to go back to C, so go back the way I came, then I also go back up in the tree. So the idea is that in the graph, whenever I take a step, if it's not going back on the edge I just came in, then I go down the tree. But if I go back, I go up the tree. And basically what we're going to use this is to show that, well, we're going to count combinatorial questions, like in this infinite graph. We're going to ask, well, how many paths start at the root and have some length go back to the root? How many passes of length 4? Maybe you can go from A to B and back to A, or A to B to C and back to B and back to A, and all the options. We're going to do this calculation for this tree, and we're going to argue whether for the graph it's going to be at least this number, maybe more, but at least this number, because any walk in the graph corresponds to a walk in the tree. And if I return to the same node in the tree, in particular, I'm going to return to the same node in the graph, but not necessarily the other way around, because the graph might have short cycles that the tree doesn't have. But we're going to use this to count, or to this lower bound, closed walks in this graph. And we're going to say that's going to be the crucial property that we need to be able to prove this theorem, this Elan-O'Connor theorem. So again, we're going to do that next time, but I just want to pinpoint this, because that's going to be the main way we're going to connect the deregular infinite tree to this case. And also, along the way, the proof here will also give us actually an alternative proof for this infinite tree. So it'll be another way of proving that. But I think now is a good point to stop. So are there any questions? So maybe just to summarize, so what we did today is, for the most part, we define this deregular infinite tree. We define what does it mean to understand the spectrum of infinite graphs. We prove that the spectrum of the deregular infinite tree is bounded in some interval of plus or minus 2D minus 1. And in fact, you can actually verify that you can actually get to 2D minus 1 by the examples we constructed. And yeah, and then we just started discussing how to connect the infinite tree to final graphs. But we're going to see much more of that next time. Yeah, questions? Okay, so this has no questions. So just a reminder, we're going to post the second homework later today on the website. So please stay tuned for that. And it's going to be due in 2 weeks. So let me stop the recording.